Welcome everybody. This is the Practical AI and Unity talk. My name is Emil. I go by the handle of AngryAnt on the interwebs. It's also the name of my little freelance company. That's a photo of me when I'm smiling. I work as a freelance developer. I also produce a bit of middleware, which is available on the Unity Asset Store. And I specialize in artificial intelligence. Aside from that, I used to work for Unity for 4 years and used the tool a bit before that. So I also have that going for me, which is part of the freelance setup as well. So in this talk, I'm going to go over some tools for doing behavior logic in Unity, which include HFSM, BT, and utility, which unfortunately does not have an awesome abbreviation. And if there's time for it, I'll have some other stuff at the end. So this talk is going to be very example focused, and it was originally designed for running for 1 hour, and now we have half an hour. So I'll go over the high level of the examples, and then we have 20 minutes for questions. So if you want me to go in depth in some of these examples, we can do that then. Also, this entire presentation and all the examples are available right there. I'll jump back to that slide at the end of the talk as well. So this is my sales pitch. So that's Behave, the middleware I'm developing and I have available on the Asset Store. This does most of the stuff that I'm presenting here today. So if you'd rather not write that yourself, you can just buy that thing. And that's the end of the sales pitch. Okay, so let's go into decision logic. And to start off, we'll talk about HFSM. But to let you in easy on that, let's just start with FSM. So FSM is finite state machines, and those of you who are programming inclined will probably have picked this up in university or something like that. And basically, finite state machines are groups of behavior logic or states which are connected by transitions, and these transitions consist of trigger logic. So something happens which triggers the transition, and that moves to a different state, and also it can do some sort of adaptation. So basically, in the example of a shooter, you might have an AI character that's patrolling around, looking for targets, and then the event of spotting a target happens, or the character comes under fire. That will trigger a transition that has the character move from a patrolling state into an attacking state, an aggressive state, and that might include some adaptations like crouching or choosing a different animation set, that sort of thing. So where does the H part come in? Well, basically, finite state machines are groups of behavior logic, and state machines by themselves are also behavior logic. So that's basically it. So hierarchical state machines are state machines of state machines. This is particularly useful when you have when you get to a certain level of complexity with state machines, because you end up with a lot of, for instance, combat-related states which share a lot of transitions out of combat and into a more passive state, for instance. And by having that in a sub-state machine, you end up with a lot less complexity by sharing all these transitions. So this gives you a better overview. Instead of having one big state machine that's kind of a spaghetti code setup, you can dive in level of detail. and yeah, less duplication of transitions, and in general, less mess. So let's have a visual example. Okay. So you might have a survive state. This is very typical high level of what an action combat character would have. Some sort of survive state, a combat state, and a patrol state, or a more passive state. Oftentimes the patrol state is also referred to as idle, but since characters standing around doing nothing are generally quite boring, usually most games will default to having that be a patrol sort of state. So you'll then have under the survive state, like the survive state could then have like different types of substates, different parts to surviving. First, if you're in a survive state, so the survive state could be you're low on health, or like there are too many enemies, that sort of thing. You might have first a state of escaping whatever danger is currently threatening you, and once you're escaped immediate danger, you would probably want to heal up, and then go back to your survive state. At which point you can go back to patrolling, looking for targets, and you can end up in combat, which might put you back in survive if things go bad, and so forth. So at this point, we only have a few states, but you can imagine if these states were not grouped together and patrol and combat started getting a lot of additional states, you can imagine this would grow quite significantly and be less interesting to have to keep track of. So let's jump back in here. Right, so let's look at some source examples of this. I have a few patterns that I like to use when I code this from scratch. And yeah, the first one is this enum delegate pattern. So again, I'm just going to go over the high level of it, and then we can dive in to detail later. But the basic idea is that you can see that fine, yeah. Basic idea is you have a bunch of states specified in an enum, and those are then mapped to functions. And then on each AI update, you basically execute the current function that's mapped to the current value, state value. So you can see in the start state here, we start with the first value of the enum being the current state, and then that means we execute the update start state function initially. That will log out a message and then set the current state to running. The effect of that being that now, whenever we call the current state, we will instead be executing the running state function, which will iterate for 3 times, log out a message, and then switch to the end state. And that's basically it. So behind this is a dictionary holding basically delegate references, or delegates are the C# version of function pointers. So basically a dictionary of enums indexing these function pointers, and then you have the current state, which is the enum variable, and you just execute whatever is pointed at that whenever you do an AI update. And this is, in this example, handled by reflection, which we can look at later. So the next example is coroutine-based. So coroutines in Unity are basically a way of doing pseudo async stuff without getting into the mess of threading. So you can execute some functionality over time, and then say you're building up some state or some units or whatever. You can start building them up, then you can yield for a while, wait for the rest of the game to actually execute, and then come back to whatever you're doing. So this is of course great in AI because you want to do stuff over time. You want to have a state that does things as like, walking around patrolling, for instance, waiting until you arrive at your goal, that sort of thing. It also means you can get more standalone logic because basically, if in the previous example, the state variables were held, the state-specific variables were held on the class. You can see we have in the running state here, we have the run counter, which is a member variable, and you can imagine if you start growing a lot of local state variables per state variables, the local variables for this class are going to explode quite a bit. But when you use coroutines, you can have local variables persist over time without having them have to be member variables of the class. So less mess again. And yeah, this gives you this clear separation that you have the agent class executing the system, and then you have these separate islands of functionality for the state. So this is an example of using coroutines. In this case, we're not using the dictionary enum setup that we used before. Instead, I simply have a current routine variable, which is of a delegate type. So where before we were setting an enum variable, I'm simply setting the value of that delegate variable to, in this case, the running state function, and in that case, the end state function. So it's executing the same way, except this time we are, if you recall in the first example, we're just running this loop and we're waiting for the next AI update. In this example here, we're yielding until the next time this coroutine comes around, and that way we can better control exactly the sort of wait times we want. Yeah, and that is basically the difference. So a variant on this is having explicit transitions. So as you saw in the previous example, basically all the transition logic and the transference or adaptation logic was inside of the state coroutine. So alternatively, you can basically have explicit transition handlers, which encapsulate the transition logic and does the adaptation. So if you have a lot of transitions, the former version will quickly end up with a very big state functions for handling all the different transitions and all the logic associated with that. If you offload that, you get back with a much more manageable set of state functions with the explicit transitions handled elsewhere. So yeah, the more complex you get a lot easier, and it's a more formal format. So if you later add changes to how transitions are handled, or you want to do something specific for all these types of transitions, you can make more assumptions about how the existing or the rest of the system works. So assumptions are, it's a popular thing to say that assumptions are bad, but in some cases they're good. So here's an example of that. Let's see here. So in the start state, I basically, instead of setting a variable, a transition variable, and then yielding some time or whatever, I yield a transition to type. And this type lets me specify which state do I want to transition to, and which type of transition should I use. So by having this type of transition abstraction, I can also group together transition types. So if I have general types of, okay, this is a compat type transition, so that usually means I want minimal delay, I want priority execution, um, specific interaction with the animation system, audio systems, that sort of thing. You can group them together fairly easily. So I quite like having that level of abstraction. And you know, if you don't need it, you can just always use default transition and change it later. Again, with the assumption there. So it's the same machine. We're doing a start state, then we're telling the system to transition to the running state using the default transition. And in the running state, we're running 3 times, waiting, and then transition into the end state, again with the default transition. So here's the implementation of that default transition, where I'm simply logging out that we're doing this transition, and then just to showcase a bit of spatial casing, that if the transition or the state we're transitioning from happens to be the running state, then we'll just reset the run counter. But again, yeah, just an abstract example. Okay. And yeah, I mean, all this stuff, please ask questions later if you want more detail on it. Right, so that was not too much magic. On to behavior trees. So, where hierarchical state machines are transition selecting groups of behavior logic, behavior trees are instead trees regulating flows of actions. So that's basically it. We can skip to the end of the presentation or for this, but let's go into a bit more detail on that. Behavior trees, instead of being this random graph of nodes going all over the place, behavior trees are very structured, top-down kind of beast. So you have basically the layout of starting execution at the top, and then you branch out through your designed behavior trees and end up with leaf nodes. The leaf nodes being actual actions to be performed, such as fire the weapon, switch to the crouch animation, the crouch states, fire off a pathfinding request, that sort of thing. And in between the first node, or the entry point, and the leaf nodes, you have this tree structure created from control nodes. And basically, execution in the tree runs by switching from node to node, and then each node returning success or failure state. A success state meaning, well, success, and otherwise failure. Alternatively, a lot of setups also have a running state, which basically means once you yield that tree state, you can go back and basically execute that branch again because there's more work to be done. And the nice thing about this setup versus the state machine setup is that you have a very limited number of control node types, so it's quite easy to read. You very easily, if you, for instance, transition control of a group of behavior trees from one developer to another, it's a lot easier for that receiving developer to get an overview of what's actually going on here versus some big convoluted state machine where there's a lot of hidden information. Behavior trees are, in this regard, easier to parse. So yeah, transitions are implicit. You don't have to go in and specify exactly how to jump from one branch to another. That arises from the structure of the tree, and basically, since the tree evaluates from left to right, just by moving the children in a tree, you can switch priority of actions. And this also means that you can very easily recombine behavior trees, take parts of behavior trees, put into others to quickly expand their functionality. Whereas in a state machine setup, you again have all this hidden information and most likely will have to do a lot of adaptation code to reach that same point. And yeah, this means the more behavior trees you build, basically the more you can reuse and expand your system. So generally, it's a good idea to define abstract behavior trees in order to be able to recombine them later in more specific ones. Yeah. Some downsides to behavior trees versus state machines are you don't have as tight control over behavior trees as you do with state machines. Basically, in a state machine, you can make any sort of transition you want and do it at any time you like, whereas behavior trees are tied down to the actual authored structure. Of course, so yeah, finite state machines have a tighter control, and of course, the most tight control you get is by scripting all your AI. But then you're sacrificing control, or you're sacrificing productivity for control. So basically, there's no. I'm a huge fan of combining everything. There's no one tool to rule them all, so I usually combine all this stuff together. So that's a lot of text. Let's look at a visual example of a behavior tree. So very often at the very root of a behavior tree, you have a selector. The way the selector is executed is under the selector, you'll have a bunch of child nodes or child branches. And the selector will execute from left to right each branch. And the first branch that returns a success value will be the selected one. And then at that point, the selector will succeed. If a child returns failure, the selector will go on to the next child. And if all children return failure, then the selector itself will return failure. So the reason why this is usually the root node of a behavior tree is, again, if we're doing the same setup we had with the state machine setup, we have the survival branch or the survival subtree. We have the combat subtree and we have the patrol subtree. Now we only want to do one of these things. So basically, if we don't need to do any sort of survival stuff, then survival should return failure, which will cause the selector to go, okay, well then I'll switch to the next one and see if I can do that. And if there's no combat to do, you have no targets, you have no weapon, whatever the case might be, combat might return failure, at which point, well, okay, then I should probably go find a target. So then we go patrol. And then patrol will succeed at some point, or it will fail. Say if a target is found or you're unable to patrol. At this point, since this is at the most top level, whether the patrol subtree returns success or failure actually doesn't matter to the execution of the tree, but your system executing the behavior tree might want to handle a success-failure return value differently. So these are if we're continuing with this example, the survival and the combat and the patrol subtree would be sequences. So let's just connect those up. The way sequences work, and sequence is a different type of control node. A sequence, just like the selector, executes from left to right, but unlike the selector, the sequence wants all of its children to succeed. It's a very happy control node, or demanding, I guess. So basically, if a child succeeds, then the selector then the sequence will continue on to the next child. And if all the children succeed, the sequence will return success itself. If any of the children fail, the sequence will stop evaluating children at that point and itself return failure. So in the case of our survival branch here, we probably want to, as the first thing, do a wounded check. So is this character wounded? Do we need to do some sort of survival action? If we're not wounded, then we should just return failure, which will cause the sequence to return failure. and that will cause the selector to move on to the next sequence or the next child. In this case, that's combat. But if we are wounded, then we should return success here, causing the sequence to go on to the next child. And then we might have something interesting like go get a health pack to bandage your wounds. And similarly, in the combat section, we only really want to do combat if we have a target. So if we don't have a target, we return failure. That propagates up and it goes over to patrol. But if we do have a target, then we should attack that. And finally, in the patrol setup, we should go to the target we have and then target a patrol point. So a small detail here. The reason why I didn't flip those around is because you get a bit more interesting behavior out of this order, like versus. So this is the more intuitive setup that you would first target a patrol point and then go to that target. But the behavior you get here is, well, the last target we have is either a patrol point or it's the last thing we attacked. So by having it this way around, you prioritize going to whatever current target is, which could be the last character you attacked, which yields some interesting behavior. So you're not completely locked into this patrol point grid. You get some, like, go over and investigate whatever you just shot dead. So yeah, let's jump back and find some more stuff. A source example of behavior trees. This is again implemented with a coroutine setup. This is somewhat more complicated because there's all this handling for different control nodes. But basically, we have a root coroutine function that, when executed, basically runs the tree. So in this case, we have a sequence at the root, and so these are parameters. The parameters to the sequence function that is a coroutine that gets returned. So first we'll log out. We'll call the log action function with the a parameter. Then we'll do a sequence where we're again executing the log action 3 times. Then we're executing the count action 3 times, and then selecting. Then running a selector with pass action 3 times, taking the parameter values of failure, success, and failure. So the execution of this will be, we log out the action, then we log these things out, then we run this action, and then, since this is a selector, we will only run the first and the second one, because as a value of success will cause the selector to immediately disengage. And the way I've set it up here is the coroutines for running actions will have to first yield back to the system a data type. So this data type is kind of a container you can use for state and for reset handling. But the log action doesn't have anything to do. It doesn't have anything to initialize. So we'll just yield null there, then log out our message and yield success. Pass action will yield whatever it was asked to yield after logging it out. And then, again, it doesn't have any initialization. Now, the count action, on the other hand, does have some node data. Now, this is useful for instance, you can have in certain implementations of behavior trees, you can have branches or subtrees be interrupted. Okay. So we're running a bit over time soon. You can have subtrees be interrupted, and in that case, you should probably want to gracefully reset that. So in this case, in the first init set, we create our node data, yield that data, and then in our counter loop, we will check if we should reset, and then break, and also break if we've reached our count. Otherwise, we should just log out the current count and return running, thus telling the tree that we have more stuff to do. And at the end, we'll just succeed. So, yeah, so we're all skating on this. But I have one last thing I'll run through very quickly. That's utility. So utility is from the world of finance. Basically, the idea is it's a way of calculating the usefulness of actions. And one of the most powerful things you can do with utility is you can normalize values from different spaces. An example of that being, if you're buying a car, you might think about buying a Tesla, because that's a lovely car, or a fast petrol-based car. So how do you, aside from mileage and speed and all that, there are some things that you can't directly compare. Like the downside of having to charge the Tesla, versus the emissions from the petrol-based car. So how do you define that? Well, you set up some curves and graphs to kind of intuitively arrive at some comparison value. So, for instance, this might be a utility curve for the main party this evening. So this is the utility for getting another drink. Initially, everyone wants to get a drink, and then as the evening progresses and people get tired, that becomes a bit less useful. However, discussion confidence will follow a slightly different path, which might not necessarily follow the same path as the discussion value as you get towards the end of the evening. Okay, party mention. So let's do a very brief graph example. So as I mentioned, utility has curves and alternatively graphs. So say we have to compare, we have to arrive at some value of current threat. So we have a number of enemies, and we have our own health. So how do we compare, how do we arrive at a threat value based on enemies and health? It's not really, you can't really compare those numbers directly. So how about we take and say, instead we'll just count the value of woundedness, and let's see here, and scale that by 10, because let's see here, and then we can compare those two. And this is completely arbitrary. This might be something that works for that particular game. And it might not work at all for another setup. But this gives you some way, this gives the game some way of comparing these two arbitrary setups. So let's see if we can quickly fit in a source example of this. So this is the health and enemy comparison we had before. We have our health variable, we have our enemies count. And we want to determine some level of panic, so we'll create an animation curve for that. So the stress that we just defined before is, again, we're taking the amount of damagedness rather than health, multiplying that by 10, and returning the maximum between that and the number of enemies. And then taking in curves, we can just evaluate the curve that we defined between 0 and 10, 10 being the absolute maximum level of or value where we're completely panicked. So 10 enemies would panic us, or being completely dead would panic as well. So in order to determine a level of panic, we basically just evaluate that curve based on the amount of stress that we just calculated. So in Unity, by making this animation curve a public variable, I get a nice, let's see here. I get a nice editor for quickly specifying it. So I'll just quickly show that. Utility, example one. So you can see I have the health value here and my panic curve. So as we get more and more towards 10 enemies or fully dead, we want to panic more or reach a value of 1 unit of panic. And basically, we could then have a threshold value set up around 0.5, at which point we should flee or execute different animations, what have you. So yeah, that's practical utility. And jumping back quickly. Don't save that. Okay, so this was my marker for if I have time for stuff. Since I'm over time, I don't think I do. So we'll just switch to questions. And that's what I had. Thank you.
Hey there. One question I had regarding behavior trees is, let's say we had an animal in our game that wanted to search for food, so he had to walk somewhere, and along the way he wanted to sniff for food as well. So that's 2 actions that need to be run concurrently.
Yeah.
How would a behavior tree choose for that?
So different implementations do it differently. I like to have a parallel node control type or control node type, which basically does exactly that. It doesn't do any threading, but it executes every AI update, executes the left subtree, and then the right subtree, or whichever number, but still executing left to right, but not waiting for an AI iteration for it. So yeah.
Thanks.
Okay, well, if there are no more questions, I'll just put up the slide with the download link. So you can, yeah, both the whole presentation is one big Unity project, so that holds the slides and the example code. And yeah, that's it.